Okay, so we are going to start today's session. Hope you all can see my screen. Can I get some confirmation?
Yeah.
Okay, thank you. Okay, so today's session is about deep learning. I believe that you must have heard about neural networks in the past sessions. So, what is a simple neural network? Like, what is the basic of a neural network? A simple neural network, or you may say perceptron, it is based on the human mind, like how we learn something. You remember when you start as a kid, so when you want to like teach some kid, you want to say, okay, learn that this is apple, this is banana, this is orange. So you have to tell them again and again, right? If you tell them once in a year that this is apple, so they won't be able to recognize after 1 year. You have to keep these things in their memory. So like this concept, this neural network works. What is the main architecture here? This is a simple one having only one neuron. Okay, so here we have some inputs x1, x2, xn. These represent the different features of the input data. Like if you have a single data point, then it can have many features, like many x values. So these are those input features. And then in the neuron, we have two main things. One is integration function and another is activation function. So the integration function is mostly the summation function. What it will do? It will sum over. Now these there will be some weights associated with these input features. So it will do the summation over the input features, like W is equal to W into X. The important thing, which is the like activation function, activation function. So to bring non-linearity into the model, we use activation function. Okay, so this activation function will be applied to this weighted sum, and then it will give some output. So now we go to the different kind of activation function, different types. One type is simple linear activation function. Okay, but as we want to introduce non-linearity into the model, so this is not used very commonly. Okay, then we have some non-linear activation function like sigmoid, tanh, ReLU, leaky ReLU. Okay, they are commonly used in these layers of neural networks. So these in between neuron layers, these are called hidden layers. So we have an output layer. These are hidden layers, and we have an output layer. Input, hidden layer, output layer. Now this is a simple neural network. Imagine you can have as many as neurons you want. Like here you have only one, so you can have 10, 50, however you want. You can also have 100 neurons here. Okay, or more than 100. Also, you can have multiple hidden layers. Okay, so like in one layer you have 50 neurons, in the another layer you have 30 neurons or 70 neurons, in the third layer you have another set of neurons. So if this all depends upon your data, how complex your data is. Okay, so these are all the hyperparameters, like how many number of neurons you have to add, how many hidden layers should be there, what could be your activation function. So as I have said that these are two kinds, linear and non-linear. Now we go into the details of these activation functions. First, linear function. Simple. Okay. As I have mentioned, this doesn't provide any functionality into the output. So it is not commonly used in the hidden layers, but this can be used in the output layer of a neural network used for regression tasks. I hope you understand the difference between regression and classification tasks. Regression task is to predict a numeric output, like if you want to predict the some value, okay, some integer value, then you have to use a like okay, this belongs to class 1 or this is the multiple. So you are giving some category to the model. So that is classification task in which you classify as one like one object or something like yes or no. If it is sex, then female or male. Okay, that goes in classification task. The another function is sigmoid function. This have this mathematical equation which ranges between 0 to 1. What is the use of this sigmoid function? Now, if you use in the hidden layers, okay, then it may suffer from vanishing gradient problem. So, how this all works? Like when you give some output here, we will come into later that it will calculate some loss function and it will back propagate. That I will come at the later part. But at that point, I will also explain the vanishing gradient problem. But somehow, this vanishing gradient problem lead to a dead neuron in our neural architecture. So this is not commonly used in the hidden layers of a neural architecture. It is mostly used in the output layer for binary classification task because it produces a probability between 0 to 1. Okay. Binary classification earlier, like yes or no, or sex, female or male, or any other things where we can have two possible outputs. Then we have this third activation function, which is tanh, and it has values between -1 to 1. Okay, this sometimes they use, but it also suffers from the same problem which I have told you earlier, vanishing gradient problem. Okay, and this also is like the function means it is like a more complex function because it contains exponentials as well. Okay, so our model have to calculate a lot of exponential functions, right? So the model could be slow with these tanh functions as well. Okay, we will see later which is the most common used activation function nowadays. Next is our softmax function. Softmax function gives you probabilities over the different classes. Okay, this is commonly used in the output of the multi-class classification task where you have more than two possible outputs like banana, apple, and orange, or more than three. Any number of classes could be there. This forms a probability distribution. Okay, and the range is between 0 to 1. As I have said, that this is used in the output layer of a neural network. But again, it also may suffer from the same vanishing gradient problem. So now we come to the mean activation function, which are used nowadays in most of the neural networks. So what is this ReLU activation function? It says if your input coming from the integration function is less than 0, then it will be 0. And after that, it will be just proportional to the input. Okay. So this function is mathematically it is simple. You can see no exponentials, nothing is there. Okay, but it also may suffer from the, it can also lead to a dead neuron, because if our it is simple and it is mostly used, but still there is some problem, like if your integration function gives you output less than 0, okay, then it will give you 0, so this will also lead to a dead neuron. But scientists found another way to use this. What is that? Leaky ReLU. So in leaky ReLU, you decide some alpha value. Okay, so if give some alpha, okay, which has very specific value, dying ReLU problem. Okay, now, okay, you can go through those in detail. So yes, function. So you have activation function. Okay, we have learned about activation functions in the hidden layer. We have learned about this integration function. Now we come at the output. What is uh, what is being like done in the output layer? So in the output layer, we calculate loss functions. What is loss function? It is simply an error function. Like it quantifies the error for a single training example. It quantifies how your prediction is different from the actual value. Okay, and if you sum over all the loss function for all the training data, then it will become your cost function. So cost function is nothing but the summation for all the input data. So this is different. Cost function is different for regression, binary classification, and multi-class classification task. For regression task, we can simply have mean square error. Okay, uh, mean square error. We can also have another cost function. Okay, like RMSE, root mean square error. For binary classification task, we have binary cross entropy. Here, n is the number of the data points, how many data points you have. Okay, and this is like your output. This one is your predicted output, y hat. This is your actual output. Okay, and for multi-class classification, in a similar way, we have j is equal to 1 to n and summation over j is equal to 1 to c. And under this, y hat is your predicted, y is your actual, and here c corresponds to the number of classes we have. Suppose we have three types of outputs in the like three types of output: apple, banana, and orange. So j will be equal to 1, 2, 3. So this loss function, this is a complex example of a loss function curve. Okay, so you can see it is difficult to, like, we want to reduce the loss function, right? We want as much as we can reduce the loss function, because that will give more accuracy. So we want to reach this minimum. But sometimes you can see that there are many local minima. This is called global minima. So there are many local minima you can see at different points. So it may happen that your model, instead of reaching local global minima, it can reach here, and then it won't know if it is global or local. Okay. So to work with this, we experiment with our inputs, with our hyperparameters. Okay. So also it depends where your initialization, like there should be initially some weights. So how do you initialize your weights? That also plays some part in what will be your output. Okay. So this is like a loss function curve, and in this we have to reach minimum. Okay, so how these like we are saying that there will be some weight initializations, but obviously we don't know the like how the input and output are related. So we will do some initialization. Okay, that will be random. We don't know. So how this will work? Like after calculating the loss and cost function, how will you give this information back to the model? You have to give this information to improve the model. So what we do, we use back propagation in neural networks. Back propagation helps to a okay to minimize this cost function. Network from input to output. Okay, we use initialization function and activation function. Then we are calculating the loss function in the output layer. Okay, then what is happening after calculating this loss function? This information is passed back to the neural network using the chain rule of derivatives. Here we are not going into the mathematical details. Okay, but yes, if you want to learn, there are like many papers and there are many videos where you can learn. During back propagation, these loss functions, their gradients will be calculated. Okay, and using these gradients, these weights and biases in the neurons will be calculated, will be updated, and again the information is passed using a forward pass. Like first you go back in the neural network architecture. Okay, then you calculate the loss function using the forward pass. Like first you go back, come, and then calculate function, then do propagation, do update those weights and biases, and then again in the forward you calculate the loss function using those updated weights and biases. So in this way, you will continue on. You will try to this loss function curve. You will try to. This is the overall architecture. So what is this vanishing propagate it back to the neural network? What happens? You also calculate the during those chain rule of derivative calculation. You also calculate the gradients of those activation functions. So what if your activation function is something like in the we have seen in the exponential it is between 0 and 1. So what will happen? Your activation function while doing derivatives, the values will become so small, and when you are propagating through chain rule, so like in the first layer, you have reduced the derivative value is less. So when we go back to the next hidden layer, the value will become smaller. And if you have many hidden layers, it may happen that it will become 0. Okay, so this is the overall concept, overview of the vanishing gradient problem. So that doesn't happen with leaky ReLU or ReLU activation functions. So these that is the most common type of activation function we use in neural network nowadays. Okay, so another important hyperparameter in this deep neural network is learning rate, eta value. So what is this learning rate? This is the weight updation formula. Okay, this is the older weight, this is the new weight, and this is the gradient of the loss function. As I was saying that we calculate it to update the weights, and we multiply this with some learning rate. Now, this learning rate should be chosen very carefully because you can imagine if this is our loss curve J, okay, so you can see if your learning rate is too slow, too low, okay, it will take a lot of time to reach the minimum. And this is like a simple curve where you have loss function like this, but I have shown you a complicated one. Imagine if your learning rate is too low, it may never reach minimum. Especially you can imagine like if you have some flat curve in between in this curve, like if you have some flat thing, so if you are going slow, your loss function won't be changing much, so your model will say okay, this is our minimum. Okay, but that is not the case, this is not our minimum. And if it is too high, so it can happen that it will skip the minimum, it will just jump over here and there in the loss function curve, but it will never reach this minimum. So this is the right one, like the optimal learning rate. But how to get this optimal learning rate? You have to try with different hyperparameters. And now we have different kinds of learning rate. So you can choose. There is one called step learning rate. Okay. So your rate is changed after for few time steps. Okay. Then there are many variation of learning rate you can imagine. You can say, okay, initially you will set the learning rate to a high value, but as soon as your model is like calculating those loss functions and doing those things, when you see that your loss function is like reaching some time steps, okay, then you can also lower the learning rate. You can also set some alpha value for the learning rate. Okay, as soon as the model is reaching this epoch, or if the model value loss function value is not changing even after 10 epochs, then change the learning rate, either increase or decrease. That will depend how you are like, what do you want to do, how is your data looks like. So this is all hyperparameters tuning you can do in neural networks. So up to now we have learned hyperparameters. We can do what are the hyperparameters till now we have learned in neural networks. It is the activation function. We can use different activation functions. We can use the different number of neurons in the hidden layers. The number of hidden layers is itself an hyperparameters. How many hidden layers you want? One, two, three, four, five. And another one is this learning rate. Okay, this is another hyperparameter. And then we have recurrent neural network. Up to now, we have learned the simple neural networks. Okay, so that was the ANN that we call ANN, artificial neural network. Now we go to another branch of this recurrent neural network. Up to now, what we were doing, these are all called feed forward neural networks. We are giving some information, passing, getting the output. But for a sequential data, for a time series data, your data will depend upon the previous timestamp as well. Like if you have some weather data, so your today's weather could depend upon your yesterday's weather. Okay, you can't just take like today's humidity, today's temperature, today's like all things and calculate your prediction for the today's weather, if it is rainy or not rainy. Okay, but you also need yesterday's data. So to take this into account, we use the recurrent neural network. Okay, these are, as I have said, these are used for temporal problems. The example I have given, that was only like a normal problem. Okay, not normal. I would say that one is, if it is rain or not, that is more like binary classification problem. But you can also use this in NLP tasks, right? In language translation. because in language also you will need the previous input. You can't just decide on, okay, if you have been given like some input like thank you, okay, so you can't just translate it for thank and you in any language. If you want to translate, like in Hindi we say dhanyavad for thank you. In thank you we have different, but you get it to one word, dhanyavad. And there are many other examples, okay, you can imagine. So yes, this recurrent neural network is good for temporal problems. Okay, and this is incorporated into popular applications such as Siri, voice recognition. They are distinguished by their memory as they take information from prior inputs to influence the current input and output. As I have said, you need yesterday's data to predict, and also you need today's data as well if it is rain or not. Okay, you need today's data as well, and you need previous day's data also. So what is the architecture of this RNN? We have some input sequence, okay, like x1, x2, x3. This is some sequential data point. Now, what is happening at each time step? There will be some hidden state. Okay, this hidden state will be updated based on this is the current input at time step xt minus 1. Okay, and the previous hidden state. For example, in this, let's take this one. So this ht will be updated depending upon this current input xt and the previous hidden state ht minus 1. So how we can write this hidden state? This is some activation function for the hidden layers. Okay, and v, it is coming from the previous timestamps, some weights. Okay, and it will be multiplied with this ht minus 1, and then we have this input u into xt plus some bias. Okay, and how the output will be calculated? So now at each timestamp we have some output calculation. So again we have some activation function, then we have this weight multiplied by this hidden state plus some bias. So these arrows like looping back from the hidden state to itself, these indicate the recurrent connections. Okay, so these hidden states, these will allow you to carry the information across the timestamps. Okay, these hidden states will get updated at each timestamps, and they will play a part in predicting your output at various timestamps. So what is the difference between this recurrent neural network and the previously we have studied that was called feed forward neural network? This is mainly to handle sequential data. That one more that couldn't handle sequential data. It has some hidden state which is updated at each timestamp. But in the previous in ANN, we have seen that there was no such concept of hidden state. Okay, it can retain the memory of previous inputs using that hidden state, but here we don't have that memory of past input data points. The back propagation is also different and a bit more complex in a recurrent neural network because we have this back propagation through time, not just we go back propagate only through the hidden layers. Okay, so this is more complex, this is less complex. This is used for time series prediction, language translation, speak recognition, and here we can have image classification or regression tasks. So now we have different types of RNNs. So you have read about this one to one, one to many. We use this in another context as well. Here we have different kind of RNN. First is one to one. So here we have single input and single output. Suppose image classification. So one image is classified into one category. Okay. Then we have one to many. A single input can lead to a sequence of outputs. For example, we want to do image captioning. We are giving one input and we are asking the model to generate its caption. So it is one to many. Now next is many to one. In this, we have multiple inputs and a single output. For example, sentiment analysis. In sentiment analysis, you can have long sentences, okay, and then you have to predict the sentiment if it is neutral, negative, or positive. So output is single. Then we have many to many. In this, we have multiple inputs and multiple outputs. Machine translation um, is a proper example to for this many to many, where we give multiple inputs, but we don't know which input will give output to which word. The sequence may change from the input to output. So next we come to this bidirectional RNN. This is another variation of RNN, an improvised version and improved version, you can say. What it does, as maybe the name, from the name also you can guess what it is. It will process the data sequence from both forward and backward layer of the hidden layers. Okay, the forward layer is simply just as we have explained. That one was forward layer. You take the data from the previous timestamps also and the current timestamp also, and then you give some prediction. What happens in the backward layer? It will process the data from the output and the future hidden state. Both layers, it will be values. Okay, so this is called bidirection, which works in both forward and backward pass. So its architecture is same, but in forward pass it will process the sequence from beginning to end. Then we have another thing included, which is backward pass, and it will process the sequence from end to beginning. And in the output, we can have combination of both the passes. So here the main application is where you the context from the past and future words is important. You can say for the sentiment analysis, you want to know the past also and you want to know the future sentences also, future elements total. So this is we are coming to LSTM. LSTM is a type of RNN, but it it has the capability of handling the vanishing gradient problem faced by RNN. Now RNN can also have same problem. Okay. Also, it helps is like in RNN, you can't have long-term dependencies due to this vanishing gradient. You can't say, okay, uh, you can't remember the past like 100 words. If it is an NLP task, you say, okay, we give 100 words and the RNN will remember, will take the hidden states and update those for those sequence of 100 words. Okay, and then give us some output. It will be difficult. So this problem is somehow managed by LSTM. Okay, this LSTM introduce some memory cells which can hold information for long period of time. Okay, and this has some process which can allow it to process the entire sequence of data, not just the individual data points like we were doing earlier. So application of LSTM is language translation, okay, text generation, and time series forecasting. It is good for time series forecasting. What is the architecture of this LSTM? Here we have three main parts. this first one, this shows whether the information coming from the previous timestamp should be remembered or we can forget it or is this irrelevant. Okay, so this will update its state. Now, in the second part, this will try to learn new information from the input. Okay, and at last, in the third part, this cell pass the updated information from this current timestamp to the next timestamp. Okay, so these are three main parts in an LSTM cell. Okay, this one LSTM cycle is considered as single time step, and this is called an LSTM cell. These three parts are called gates. The first one is forget gate, second is input gate, and the last one is output gate. So what is it doing? Input gate, what it does, it controls what information should be added to the memory cell. Okay, if the information from previous should be remembered or can be forgotten. Then this forget gate controls, this input gate controls what information should be added to the memory cell. Okay, and then what this output gate is doing? It is like controls what is the output from this memory cell. It will update the information. So this will become a LSTM cell. It will maintain a hidden state which acts as short-term memory of the network, and this is updated at different timestamps. Okay, so because of this LSTM cell, like it will hold memory for longer time. This is better for longer sequences. You can say for machine learning where we need the context of sentences, like what the person wants or how the sentence is giving you the sentiment, how it is presenting. So this is also same like we have bidirectional RNN. So it is the same thing. We can have bidirectional LSTM as well. In this we have forward LSTM, process the sequence from beginning to end. And then we have backward from end to beginning. And then we have combination to predict the final output. So, okay, this is for like our basic architecture. So first we have in a neural network, activation functions, learning rate, loss, and you can ask. Otherwise, I will go to the coding part, how we use all this. Coding is much simpler than the mathematical information. Nowadays, understanding how this all works is difficult then because in coding you can just call these models directly from the libraries. Okay, you just need to change the hyperparameters. You just need to work around those depending upon your data. So if there are no questions, I can go to the coding part. Okay, so we do some the part, do some calculation with the changing the activation functions, how activation function play a part in predicting the output. Okay, so here we consider a simple neural network, which I was saying like ANN, artificial sessions, Jyoti has talked about all these libraries and you are now familiar with these. Okay, so we are loading this data. This is data from Kaggle, famous Titanic data set. I don't know if you have heard about it or not. So this Titanic data set has all these columns like passenger ID, who is survived, what was the name, sex, age, and ticket number, how much fare, cabin, and from which port he has taken the ship. Okay, so these are the different input features. You can see the details in this link if you want to learn more about this data set. Okay, and here are many models are discussed. If you go to Kaggle, then you can already see that you can have many workbooks. People have done a lot of work in this data set. Okay, so you can check these. So in this, we what is our output? Our output is this to predict if the person is survived or not. Okay, this is our output, and all these are our input features. Now let's do some pre-processing. We have some, as you can see, the total is 891 entries, but here are some missing values in age. Okay, then we have some missing values in cabin and embarked. So what we can do, okay, we have 891 in fare, I guess this one is not needed. Okay, 891 itself, there are no none values. So first we fill the missing values for the age, as it is some number, we fill with the medium, and for embarked, you can see it is some categorical value. Categorical variables, you can't directly give it to the model, those categorical variables. You have to first do some encoding. So here we are doing label encoding for these two categories, sex and embarked. And also you can drop this like I think I have forgot to return, but I had dropped this column cabin because it has 204 values, 204 non null values. You can't fill it randomly with any other values. So if you see some data which has more than 50% data is missing, it's better to remove those columns. Okay, and not to give any, not to fill the missing values with some choices like median or some other choices. There could be many other possible techniques to fill these missing values. So as I have said that these data will be dropped. Passenger ID we don't need, we don't need name, we don't need ticket, and also as I said that cabin has only 204 values, so we can safely drop this column as well. Then after dropping this, we have our data, and then we say X and Y. So what was our output column? Survived, that we say Y, and the another columns except survived will go into X. And next we split into training and testing, keeping 80-20 percentage, and we perform some normalization. Okay, we use standard scaling here to do the scaling part. As you know, that scaling part is also important because suppose your age has range from say zero, not zero, age from 1 year to 60 years, and on the other hand, your Another values could have some other range, like some could have values only between 0 to 10 or 0 to 1. So you can't directly give this data to the model, because then it will put different kind of emphasis depending upon the values. It may not consider those low values, those ranges with low values. So to make it equally, so that our all input features will have equal footage, equal footing. So we do this scaling. There are another ways of scaling also. Here we are doing standard scaling. So yes, this is the main part. Here we are building some sequential model, some neural architecture. Okay, so what you do, first you call the sequential. Okay, from where you are calling this, from TensorFlow Keras library. Okay, so here you are calling this. Then okay, 16. 16 is like how many input features you have, and you are defining activation function in the first layer. Then in the second layer you have 8 neurons. Activation function is tan h. And in the final layer, because this is a binary classification task, right? And for binary classification task, we know that output should be a the activation function in the output layer should be a sigmoid function. So in the output layer, we are giving this sigmoid function, and then we are compiling the model with using these optimizers. We have not discussed optimizers in this module. Okay, so it is another parameter, hyperparameter, which is important for these neural networks. And nowadays, ADAM is the most commonly used because it changes the learning rate, and there are other quantities, weight and biases updation is also different in this ADAM optimizers. So yes, this is the most common optimizer we have been being used these days. And the metrics we are using is accuracy. We are training the model with 50 epochs, and batch size is 32. Okay, and yes, this is training, and then we are evaluating. So I have run this model. It will take a lot time to run. Okay, at least I think it took me approx 10 minutes, 10 to, yes, 10 minutes approx. So you can see at each timestamp we have this loss function is calculated, accuracy is calculated, and then validation loss and validation accuracy. Okay, so as you go with the epochs, you can see your loss is slowly decreasing. At start it was something 0.6707, and your accuracy was this. Okay, and your validation loss and validation accuracy. So you can see how this loss is decreasing with the increasing with each timestamp. Sorry, with each epoch. So at last, we are fitting it on the model. We have evaluated on our test data set, because the main thing we need to do is we need to also check our models how it is working on our test data sets. Okay. Mm, so you can see our test accuracy is 81.56%. With number of epochs, you can see how our accuracy is changing, and then it is reaching this value, and the model loss is this much, like our loss is continuously decreasing. Now we can do a different variation of this. Earlier what we were doing, we had one ReLU function, then we had tanh function, then we had sigmoid function. Now what I am doing, I'm using ReLU function, and in last layer I have sigmoid function. Everything else is same. Nothing is changed. Just here, activation function is ReLU. Number of layers is same. Number of neurons in each layer is same. Just change this activation function and see how your model is giving the output. So you can see here your test accuracy is 82.12%. Earlier it was 81.56%. So you can see only making a small change, only changing that activation function, how it is changing the how it is changing the accuracy. So yes, here I have tried only with the two examples, like changing only one activation function. I think same. You can, I will provide this notebook. It is already added in the Google Drive. So you can change more. You can see like changing the numbers here, and also maybe adding more hidden layers or removing some hidden layer. How your output is changing, how your accuracy is changing with doing these changes. But yes, you must have this one, like you initialize your model, you give some input layer, and you should have some output layer. These hidden layers you can add more. Okay, but keep these so this is for neural network how it works. Next we go to the RNN. The second thing we have learned. Okay, first install all the libraries, TensorFlow, Pandas, NumPy. If they are not already present in your system, then import the libraries. And we are also importing the data. It is a Google stock data. Okay, so it has stock prices. This is also a Kaggle data set. Okay, so this has some open price, high, low, and closing price. So here are some visual representation of this data. With time, you can see how open price is changing. Okay, and yeah, histogram like open price. What is the most common value for the stocks? You can see here. For the simplicity, for now, we are considering only one column from the data to make the predictions. We will predict only for this open open column. Okay, like it had many other columns, but for now we are taking only one column to make the predictions. First, we do the scaling. Here we are using min-max scaler. We are creating some sequence. As I have said, it will need input from the previous steps also. So this sequence length, it means that previous 60 timestamps will be considered to predict the current output, to predict the current timestamp output. Okay, so we create this sequence for RNN. You can you can test with the sequence length as well, and then we are defining our x and y, like using this sequence length, using this x, predict the next value. So this will be your y. Next we are splitting the data 80-20 split. Okay, here you must remember, in a temporal data set, in time series or any other like this, you can't do a random splitting. Okay, like we have done in this one, we use those train test split function, right? But because you can't do like this. Okay, if you do random splitting, for example, you have 3 years of data. So you can't take, okay, I will be taking first 5 months of data for 1 year, and in the next year I will be taking data from June to November. Okay, you can't do like these breaks. You can do for 2 years data you can keep in training, for 1 year data you can keep in testing. Okay, like here I have mentioned do it 80-20. So first 80 data points will go into train, and the next points, the remaining 20% will go into the test. Okay, so next we build an RNN model. Again, we will use TensorFlow library for this. We import the sequential function. Also, we import this simple RNN. Okay, this is same. This is the like output layer. Here we are predicting the stock prices. So it is a part of regression task. So in the regression, you can use here activation function as linear activation function, or you need not to use any activation function. It is your choice. By default, if you use this simple RNN, okay, it will take the activation. You can see earlier we had mentioned activation function, but here we didn't. So by default, the activation function is tan hyperbolic activation function, tan H function. That is the default function in this simple RNN. So this is you have built your architecture. Okay, then you are again using this optimizer Adam. Loss is MSC. We have discussed the loss functions in the presentation in the PPT as well. So next you do the training, do some epochs, batch size, validation splits. Now um, these epochs or batch size, these are also hyperparameters, a kind of hyperparameters. So when you are testing it for your data, see how these all things are taking part, like how this all works, how with different epochs changes the accuracy of your output. So next, evaluate the model in the same way, and how to make the predictions. Here we have done this min-max scaling, right? We have run some transformations. So just to make it visually better, we have applied inverse transformations for making the plots. Okay, so yes, in this one, we are again, you can see this loss and validation loss here, and our loss is calculated as 0.0055. Okay, and if you then this is the true stock price, and we have predicted the stock price for the test split only. Like we have split the data into train and test. So for the test, we are making this prediction. Okay, model dot predict on x text test. So yes, you can see that there are still some. It is still it's a bit far from the actual data. Okay, you can try with more number of epochs or change any other hyperparameter and see how this all works out. Another variation we could do is, now this is simply model summary. Okay, so you had simple RNN. This is the shape of simple RNN. You had 50 units, 50, and in the second layer also you had 50 units. So this is the total number of parameters, like those weights and biases. How many are these in each layer? Then in the next one, you can give the activation function. By default, it was taking tan hyperbolic activation function. Now you mention that activation function should be ReLU. I'm keeping everything else same. Units are 50 and 50 only. Okay, just changing this activation function and see how the results are coming now. Everything else is same. No change, nothing. And if you go down, you can see it is 0.002. So it is, and you can see from the plots as well, it has improved a lot. So by changing this activation function, you can see the difference. Earlier, the test loss was 0.005. So now it is 0.0002. and it is predicting the stock prices well with just change in the activation function. Next, we will also try with LSTM. So again, I said that using these models is not difficult because you just need to call it from the library. Okay, so here we have this. We will simply call sequential function like we were doing earlier. Then we have this LSTM. We are taking this from TensorFlow library like we had simple RNN. Now we have LSTM. Units are kept same. Okay, input shape is sequence length and number of features. Sequence length we have kept same. Number of features in the input data we have kept one because only we have one. Then add some additional layers like we have done second layer with unit 50. And in the output we are adding some linear activation function here. You can skip this one. Okay. Then we are compiling in the same way. Optimizer is Adam, loss is MSC, and here everything is same. Epochs is same, batch size is same, everything else is same. The main difference we have included is instead of simple RNN, we are now calling LSTM. So again, we will run this and see. Earlier, I think it was 0.002, something approximately up to this value also. So this is not much changing with using LSTM. The output is approximately same here. So you can say, like if this happens with your case, so I will say keep the model to simple RNN only. Okay, maybe simple RNN is working good for your model. So you need not to go to LSTM because the complexity level will increase as you go up these models. So yes, it all depends upon your data. Okay, sometimes you a lower complexity model can work well with your data, and in other case you have to increase the level of complexity. And also you can notice if you run this model, it may not generate the same result in each output. Okay, because it is like a black box. We can't see what is happening inside. We can just give inputs and we can see the output. Actually, we can't see that loss function curve, how it is, how the actual curve is. So yes, your output may change with each run. And these are all the hyperparameters I have explained. You can work around there, see how these are changing your output. This is all from my side. Okay, if you have any doubt in anything, then you can ask. I have shared the assignments in Google Drive. You can work on those. Take your time, understand these things, and just give a try with different kind of hyperparameters, different kind of models. Like here we are using LSTM. There is another variation of RNN which is called GRU. Okay, so you can learn about that as well, how that model is different from LSTM. What are the advantages and disadvantages? So any doubts, anything you wanna ask? So tomorrow we will go to sequence models. Okay, and we will learn attention mechanism. In sequence to sequence modeling, we will see how where the RNN fail, and we can use another like variations of these to work in some applications, mostly in machine translation or like language related tasks, text based tasks. So we will learn those tomorrow. So if no one is having any doubts, maybe we can close the session. Okay, please go ahead, Faisal.
Quick.
I can't hear you. Are you saying something?
Trying to say, hear
This
me?
was the commented in chat.
Uh, how do you typically choose the number of hidden layers into your design? So yes, as I have told, like this is all you have to test. What I do, I try with the simplest one first. Choose only one layer. Okay, because as simple the model is, it is fast to run. Okay, so choose one layer and then you start increasing the number of layers and see if your output is improving. Sometimes it happens that your output doesn't improve with the increase in the hidden layers, so then you need not to increase. So it all depends how your data is, how your model is work, how your model works out. There is no particular number for this one. And also nowadays there are many pre-trained models. Okay, so mostly for some tasks we don't do the training from the scratch, like we don't build these models from the scratch. In some cases we do, but in some cases we use those pre-training models, like for image classification, image tasks. There are I hope you have heard about YOLO models that are good for real time image classification. So that is a pre-trained model. Okay, trained on Coco dataset, which has many images, approximately I think more than 1 million images, I guess. So then you train it on your data. So you need not to train your data from the scratch. Okay, so it is already trained. All the big complex architecture is included. You need to train on your data. So you again train your pre-trained data on your data set, because suppose you have some, like those data sets have many images of flowers or cars or anything. Okay, but in your data is mainly about the images of a particular kind. For example, you have um, chicken images of small chickens in some chicken house. So you need to train your model on your data set.